This is going to be a complete example of how you could use Laplace to solve an entire differential equation. We'll be using partial fractions in this example. Here's my problem. Solve y double prime minus 3y prime plus 2y is equal to e to the negative 4t with two initial conditions. What we're going to do first is take the Laplace of both sides. We're going to be able to use the linearity property to make the left-hand side easier to solve. And we're going to use our tables to look up the values for these Laplace transforms. The right-hand side is simply 1 over s plus 4. The Laplace transform of y, remember y is really y of t, is going to simply be y of s. And remember, for the time domain we use lowercase letters. For the Laplace domain we use capital letters. We're going to rewrite the Laplace transform of the second derivative of y as this, and negative 3 times the Laplace transform of the first derivative of y as this. Now from here it's just algebra. And I'm also substituting in my initial conditions. Again, with Laplace we don't have any c's to find because we use the initial conditions while we're doing our initial calculations. So what I've done is I've collected all my y(s) terms, and all my s terms, and all my constants. Now what I'm going to do is take anything that doesn't have a y(s) in it and move it to the right-hand side of the equation. And I'm going to factor out a y(s) on the left-hand side. Now what I've done is factored the s squared minus 3s plus 2, and I've combined the right-hand side into two fractions with a common denominator. Now I've gone ahead and divided both sides by s minus 2, s minus 1, as well as combined the fractions into one fraction. And now I've gone ahead and combined like terms. The way we're going to solve this is by using partial fractions, because then I will have something that looks like this. And when I have something like this, it's quite easy to find the inverse Laplace transform. And I'm just going to use the cover-up method to find a, b, and c. For a, I'm going to let s equal negative 4, and again I'll cover up the s plus 4, and when I plug in s equals negative 4, I'll get this, and when I plug in s is equal to negative 4, I get a is equal to 1 over 30. I'm going to do the same thing for b and c, and I'll get b is equal to 25 over 6, and I'll get that c is negative 16 over 5. Putting this all together, I get this as my y(s). Now I need to take the inverse Laplace transform of both sides, and using the linearity property I can rewrite the right-hand side as this, and finally y of t is this. Again, I don't have to go through and find my values for c, because with the Laplace transform the initial conditions are worked into the problem from the beginning.